open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Nghiên, Master of Science, University of Liège, Belgium. May I request the promovendus to go to the next, please. It's an honor to welcome guests for this committee from outside the TU Delft community, and therefore I extend a hearty welcome to Professor Bordas, Cardiff University, Professor Askes, University of Sheffield, Professor Luding, University of Twente. The other members of this committee are Professor Gutierrez, Professor Jan Rots, Dr. Stroeven, and the promoter Professor Sluis. My name is Professor Wieringa. I'm the Vice Rector of this university. May I request Professor Bordas to start the opposition and take the floor?
Thank you, Wieringa.
Please don't forget your so we know that you are in function. Please.
Thank you, mein Herr Director. Waarde promovendus. First of all, I'd like to congratulate you on your thesis, which I thought was very well written and attacked one of the most difficult problems in computational mechanics. And I thought it was really a pleasure to read the thesis. That was really excellent. I've got a few questions, and I'll start with one which I think will make it easy for you to get into the defense, which is about the, you say in the introduction that it is easier to actually characterize materials at the smaller scales, which means that multi-scale analysis is justified because it is easier to find material characteristics at the smaller scale. And I'd like to know, generally why you think this is the case, and if you could maybe give examples of why characterizing materials at a smaller scale is easier than at a coarse scale.
Is this question clear to you?
Meneer de Director, that is clear.
Then I give you the opportunity to vent yourself.
How clear they are, opponent. Thank you very much for your nice comments on my work. To your question, yeah, you know that all the people in computational homogenization say that finding the properties at the micro scales is easier than at the macro scale. And in my opinion, it is true, because with the heterogeneous material at the macro scale, you have to take into account the interaction between them. However, if at the micro scale, you only have to measure the properties of the single heterogeneity. And in my understanding, it's easier. Having said that, I think that micro scale is more. So to measure the properties, we have to really have advanced experimental technology. Yeah, that's my thinking about that issue.
Yes, thank you very much. I'm satisfied with this answer. Now I'm going to ask you a question about boundary conditions on the representative volume element. And so essentially with some periodicity and scale ratio requirements, the microscopic solution that you have should be representative of a full-scale direct numerical simulation of the course, of the global structure. And in your work, you select very specific boundary conditions, which I'm not going to describe because it's clear to you, and I think clear to the others also. And my question is, using the boundary conditions which are unidirectional, essentially, are you forcing one particular type of response at the micro scale, which may or may not be representative of the physical reality?
Yeah, as you know, the RV in my case is to represent for a bond in a macroscopic crack, and the crack deforms in two ways: scan opening and sliding. So that's why I enforce that boundary condition at the RVE. And since I will rotate the response of the RVE to the direction of the macro crack, so I just need that specific boundary condition at the RVE, and then I rotate it according to the orientation at the macro crack. So I don't think it's too restricted. Yeah.
Okay, what about the case when the shear band would not split completely the RVE?
To be honest, I didn't consider shear bands. I consider crack, which is usually break the RVE into two parts.
Yes.
So for your question, I simply say that I don't know. There's a future word for shear band.
Okay, so maybe one penultimate question. It's about the size of the RVE. So you have essentially a few Gauss points along the crack, and each Gauss point is represented by an RVE, which means that the sequence of these Gauss points is supposed to represent the fracture process zone.
Yeah.
Is that right?
Yeah.
So now the question is that the traction separation on one RVE is more or less a step. It's a constant.
Yeah.
So if you put all the steps together, you get a staircase.
Yeah.
And now the question is that staircase representative of a realistic material? And if so, which material? What are the restrictions posed by the fact that you have such RVEs along the crack?
Wow. Yeah, I think if you have enough Gauss bond distributed along the crack, and then you can capture a realistic distribution of the traction profile along the process zone. However, if you have more Gauss bond and you have more, then the RVE is smaller. I think there's a difficulty there. Yeah, I think so.
Okay.
Yeah.
Can you be a little bit more precise? What kind of difficulties?
The difficulty is that the RVE, especially for random materials like concrete, should be large enough to contain enough the heterogeneities, so that it is representative for the entire microstructure. But in the other hand, it must be small, so that the traction is uniform over it. So that's a difficulty. So it should be large, but it also should be small to satisfy all conditions. That's the difficulty. Yeah, I'm talking about.
Mind if I take those, or I have time for one more question? Thank you. Okay, and the last question is about the very use of material stability analysis to calculate, to predict, let's say, the propagation direction. So, although you generalized, let's say, multi-scale methods to the case of softening materials, and I have to say, probably you generalized it in a particular sense for particular cases, not in a general way. Although you did that, I still have doubts as to, let's say, the justification for the use of material stability analysis, which basically assumes that the constitutive law has, let's say, a negative slope, to put it simply, in the context of multi-scale methods, because of the fact that as soon as the tangent becomes negative, the RVEs become non-existent, although you seem to prove that in some cases it still exists. So maybe my question is a proof of my confusion about the difficulty of the approach, but I'd like to take this opportunity maybe to be enlightened. by you on why you think the loss of material stability is still valid in your cases.
Yeah, I used material, loss of stability of materials as a criterion to detect crack initiation at the macro scale. So at the micro scale, localization is detected, and then I insert a macro crack at the macro scale to regularize the macroscopic boundary value problem. And you doubt in that when the material loses its stability, the RV doesn't exist. But however, with our failure zone averaging scheme, we show that even with localization band, an RV does exist. Yeah, so I think I can use that criterion to detect crack initiation at the macro scale.
So which means you must use your own way of calculating the...
No, the other people in the field, for example, Professor Massar or Professor Velisco did just the same thing. I follow their approach. Yeah.
Are you referring to the multi-scale aggregating discontinuity method?
Yeah. Yeah. The method of Professor Velisco. So at the micro scale, when he detected loss of stability, the occurrence of localization band of cracks there, he injects a macro crack at the macroscopic landscape.
Yeah. I see the connection, but I'm not convinced it's exactly the same. Okay.
Satisfied with the answer?
Yes. Okay. Okay, I've got one final question, which is more technical. It's about the basically when you propagate the crack using XFEM, you have an old crack tip and a new crack tip, and you have now a new crack segment. Okay, which means that you have new integration points which did not exist at the previous step.
Yeah.
And you need to somehow initialize the internal variables at these integration points.
Sorry, no.
You don't?
Yeah, I made an assumption to avoid that difficulty.
Okay.
So the new integration points are assumed to behave elastically with the tangent computed from the RVE associated to the integration point at the previous step before crack initiation.
Okay, why is this a valid assumption?
Usually, in reality, we see that when you have a crack, the strain localized on that crack and the rest behave elastically. Usually, they unlock. That's the reality that I rely on for my assumption. Yeah.
All right. Okay, I'm satisfied with the answers. Thank you very much.
Thank you very much indeed, Professor Bodas. I would like to invite Professor Askas to take the floor.
Okay, meneer director. Waarde promovendus, I actually have a question about one of your propositions, proposition 4.
The candidate, do you mind to read aloud proposition 4, please, in English?
Assumptions often limit the capability of the methods that are built on them. Properly chosen ones, however, save a huge amount of computational expense.
Thank you. I may have an idea that, well actually I may have an assumption that may allow you to save a lot of computer time. What you're doing, the way I understand it, is you've got a micro sample and the cracks are always vertical. Yeah, you always load them horizontally.
More or less vertical.
Okay. But you always load them horizontally.
Yeah.
Yeah. So I was thinking, that to me is very much a one-dimensional problem. You agree with that?
Yeah.
Yeah. So if you agree with that, can we then not simply say, let's forget about all this upscaling and downscaling. Let's just test one sample once and for all, get a one-dimensional stress-strain curve out, and use that in a way of numerical homogenization. That would be a lot cheaper. Can you convince me that I'm wrong?
How clear the opponent? You're right, of course. You're right.
Oh, that's a very quick answer.
Yeah. I have a long answer now. Yes.
Go on then.
Yes, you're right. But numerical homogenization, and you know that, is not general. That's why computational homogenization were born. And why? That's because in my case, I consider monotonic increase in log-in. So I have only one.
Just begin to do it again. What did you say? I didn't quite hear that.
I only consider monotonic log-in. So I have only one localization band at micro scale. And for this scale, I can use numerical homogenization. You're right. However, if I have a non-proportional log-in, means that I have initial localization band, and then unlocked head occurs, and then the log change direction. It means that in that case I have another band due to the anisotropy of the RVE. In that case, numerical homogenization cannot apply anymore. However, my scheme based on computational homogenization can be still used.
I'm a bit confused with that because you always rotate back your loading to a pure horizontal loading. So I don't see the anisotropy in your scheme.
Excuse me, can you?
Yeah, I'll talk about it again. I'm a bit confused with what you say now, because what I understand is you always rotate the loading back to a purely horizontal loading on your micro samples.
Yeah.
Yeah. So that means the crack can only grow vertically or virtually vertically, in your words. So I don't see how your scheme can actually accommodate anisotropic or say multidirectional crack growth for your microsamples. So
yeah.
maybe another way of saying it, I don't think your scheme accounts for non-proportional loading at this stage.
Yeah, that's true.
So
and that's also addressed in my thesis. Yeah, the rotation of the RVE cannot be used for non-proportional loading.
indeed.
And for non-proportional loading, I didn't implement it, but I proposed a way to solve it. Just simply before solving the RVE micro problem, you first rotate the geometry of that RVE to align to the macro crack, and then you solve the problem.
Okay.
However, then you have to store a lot of RVE meshes, and it's expensive. That's why I didn't do it.
I understand why you did what you did, but I would say, based on the current technology which is in your thesis, numerical homogenization is a lot cheaper, you get the same results. That would be my statement.
Yeah.
Okay, we agree on that?
Yeah, I agree.
Excellent. I've got time for another question.
Yes.
Yeah. Okay, the other question I had is it's about continuity of the RVE definition. So you've got two sets of material, if you want. You've got elastic material, and then you've got softening material. And you use different RVE definitions. For the elastic material, you average over the entire microsample. Yeah. And for the softening material, you average only over the damaging part of the material. Yep. Okay. Now, there's a bit in the middle. There's the hardening, the pre-peak hardening. Yeah? And then we have to get some clarity. What happens there? I think in hardening, the RVE size grows. You need bigger microsamples to get a statistically homogeneous response.
Yeah.
Okay, so you agree. Right. So the situation we have is we've got elastic RVE, yeah, which is about a few times the aggregates. Yeah, 3, 4, 5 times the aggregates. Yeah. Then we go pre-peak hardening. The RVE grows.
Yeah.
Yeah. Then we go softening, and suddenly it collapses to a very narrow band.
Yeah.
Yeah? So I don't think there's a continuity of RV definition there. And I think because it's all continuum mechanics, it should be continuous. So I'm a bit confused. Can you help me? Do you understand my question?
Yeah, I understand it well, but it's a difficult one. Yeah, you're talking about the continuity of the RV for...
I would like that exactly at the peak, yeah, exactly at the peak, the two definitions of RV predict the same. If you take the limit case, that you're exactly at the peak, so at the peak of your load displacement curve, or at the peak of your load displacement, or stress strain on micro level, if you're at the peak, the two definitions must give the same result.
I don't think so. So,
You disagree with me?
yeah, it's dangerous, but so I think for the elastic regime, we can use a small RV. That's true. For hardened regime, we have to use a bigger one. And for Stochastic regime, we have another definition of the RVE. And I think it makes sense.
Well, you say it makes sense. You haven't explained it to me yet that it makes sense. Can you explain it to me why it makes sense?
Because the RV is why we need an RV. The RV is just a micro domain that is representative of the material that is attached at the macro scale. So, at the macro scale, if you are in the elastic regime, I can use a small RVE. However, if you are not in the pre-pit hardened regime, I have to use a bigger one. And for shortening regime, I can use another one. Because it serves for different purposes. So that's why we need different definition of RVE. That's what my humble opinion.
But my question is about the continuity of the definitions. I would like the two definitions to come together at the peak.
I can't see it that way.
What do you mean with that?
I really don't understand your statement. At the peak, why it should be the same?
Because it's continuum mechanics. And this is a smooth transition from elasticity to hardening to softening. They're all very smooth curves. So I would expect the two definitions of RV to boil together at the peak.
Continuum mechanics, I think it's just about continuum mechanics as is before RV was born. So I don't think why you relate the RV to the continuum mechanics there. I don't get your point.
So you disagree that the two definitions of RV should give the same answer at the peak?
No, I agree that if you use one single big RVE, not two RVEs for the elastic regime or the hardened regime, and then of course you get the same result if you use the big one.
Yeah.
Yeah, I agree on this.
And if you use exactly that same big RV at the peak,
Yeah.
and over the peak, does it give the same results as well?
Yeah, because for the shortened regime, we only do the averaging over the localization band. And no matter what the RV is big, we just concentrate on that band. So I think for the bigger RV, we still get the same result.
Then you've answered my question. Thank you.
Thank you, Professor Askens. I'm sure you can talk further in the reception later. I would like to invite Professor Loering to continue the conversation, please.
Dank u wel, meneer director. Waarde promovendus, I also read your thesis with interest, and I had a few questions which were not addressed yet. One of them is concerning reaction kinetics. So on page 46, equations 3.3, you have a lot of equations or rate equations for reaction kinetics, which involve some volume change of the aggregates due to chemical reaction. So how big do I have to think of these volume changes? How big are these volume changes in the real material and in your model?
How clear the opponent? So, your question is about this equation, right? The reaction kinetics. And could you repeat your question about the volume changes?
Yeah, you write something about volume change because of reaction kinetics.
Yeah.
Yes. So how big is the volume change? How 1%, 0.1%, 10% volume change?
I think the volume changes evolve in time, so I can have a specific answer to your question.
What is a typical volume change at the end of the process then, if you truly it evolves in time?
It also depends on the particular particles. These particles react much, and then the volume change is big. For the other particles, it can react less. So
what is big? Give me an idea, a quantitative idea.
It's just small detail that I didn't pay attention to it.
Maybe it's not 50% because that you would have seen optically, but a volume change of 1% you typically cannot see on the pictures on the photo.
For some particles, it's really 100%.
Some of them.
Yeah.
Okay.
Then they
So
disappear
that's
at the end of the reaction. Yeah.
Okay, so thank you. That's really big. Okay, now at the same time, chemical reactions can create heat. And what would be the volume change because of heat, because of temperature change? I think you don't have that in the model.
Yeah. I didn't include it in that model. It's not my model. This cement hydration model is not mine. I took a model, implemented it to get the microstructure, and I concentrated on the finite element modeling of the behavior. Yeah.
Okay, now I'm happy with the qualitative answer. Is it big or small as compared to the previous volume changes? Chemical reaction takes out volume or transforms volume, but temperature, how much volume change would you expect from a temperature change by 50 degrees or so? Is that big or small compared to the chemical volume changes?
I think it would be bigger, I think. Incorporating heat temperature.
Could make it bigger?
Yeah.
Yes. Okay. And then at the same time, you mentioned it already in part of your first answer, and the material in a real concrete sample, for example, or in whatever material you take, it will not be the same material mixture in one part of the system. It will be a different mixture in the other part of the system. So there are fluctuations from one half of the system to the other half of the system. What would be the effect of fluctuations? I mean, sometimes people say coarse graining, sometimes people say homogenization, sometimes people say micro-macro transition. And in your approach, what are the effect of fluctuations on the micro scale on properties on the macro scale? Did you see any, or did you rule them out from the beginning? Maybe fluctuations is the wrong word. Variations of material properties.
Yeah, we used homogenization to model the transition from the micro scale from the fluctuation due to the heterogeneities to the macro scale. We use homogenization approach.
Okay.
Yeah.
So, but homogenization for the people who don't know the mathematical background could mean to these people that you make everything homogeneous, which could be interpreted of erasing the fluctuations. This is more a philosophical question. It's not a quantitative mathematical question. Homogenization, the word homogenization means you make everything homogeneous.
Yeah.
But on the micro scale you have fluctuations.
Yeah.
So I want to have your opinion or I mean, you will probably tell me you don't make everything homogeneous. You take micro properties to the macro scale. So is that true? Or do you make everything homogeneous on the micro scale and then transport it to the macro scale?
Yeah, that's good. Yeah, yeah. I used homogenization to compute the effective properties of the macro sample. And the fluctuation was considered in the boundary conditions imposed on the RV boundary.
Okay, so there they are.
Yeah.
Yes. Okay. So thank you. Have I one more time? On equation 2.19, that's a mathematical question now. You define the strain measure as epsilon 1 square plus epsilon 2 square. Equation 2.19 on page
16.
16, yes. Further down. Okay, so the equivalent strain is epsilon 1 square plus epsilon 2 square, and from epsilon 1 and epsilon 2 you also take the positive parts only. So my question, okay, I have two questions. I ask the first one first. Why only the positive part? Why not the negative part?
Because I consider only the tensile failure.
Okay.
So the negative strain don't contribute to the tensile failure.
Okay, so this assumes that the compression strain, the anti-tensile strain, does not contribute to the material behavior. Okay.
Yeah.
And the second part is, where is epsilon 3? I mean, we are in 3 dimensions, so I would have expected to see epsilon 3 there.
Yeah, I think I said 2 dimensions. That's why.
So before we were at 1 dimension in the previous question, you practically have a almost 1-dimensional model. This is now 2-dimensional, but the real world is 3-dimensional. So
yeah, of course, the real world is 3-dimensional, but my thesis was confined to 2-dimensional problem to limit the computational expense. Yeah.
So what would be the third dimension contribution to tensile?
Then just epsilon 3
yes.
included. Yeah.
Okay, so that could be just added in 3 dimensions. That's for the next PhD
yeah.
student. Thank you. I'm satisfied with it.
Thank you, Professor Sully. Then I'd like to invite Professor Gutierrez to continue your position.
Dank u wel, meneer de rector. Laten we beginnen dus. I'm actually a bit curious about your RBE, your representative volume element, and about its size. The way you have defined it by means of the failure zone aberration technique is still, yeah, I don't really understand what's actually the size of your RBE in the end, at the end of the day. Can you help me, please?
How clear the opponent? Yeah, we said about the existence of an RBE, but you're right, we didn't know the size of an RBE. Because for this we need to do some statistical analysis, and numerical analysis is expensive. So it's a future work.
So what size have you been using in your computation?
It depends on the purpose of the examples. Yeah. For some propagation, I usually use very simple RBE to reduce the computational cost. Yeah. But for the proof of numerical proof of the existence of RBE, I use I think I can call it realistic RBE for concrete. Yeah.
Okay, so in the simple computations, the RBE would be the size of the failure processor.
Yeah.
As much small.
Yeah.
Okay, I'm happy that you also say yourself that to know what's the actual size of this RBE, you do further analysis, further studies as part of future work. I'd like to discuss this future work. You want to do more statistical analysis, and you consider that statistical analysis is the key to find what would be the proper size. You did some statistical analysis already. Find it. Yeah. page 78, you're comparing the expectation and the deviation of the fracture energy using standard averaging and using failure averaging. You conclude from this picture clearly that standard averaging is not leading to an RBE because expectation is going down as the size of the expression grows. For failure averaging, you conclude that the mean value doesn't really fluctuate, it remains more or less the same. And you also state that the deviation is reduced as the size of the sample grows. Can you, however, explain to me what's happening for the sample size of 15 millimeters? Why do you have that big drop of deviation for 15 millimeters?
Yeah, I did a statistical analysis. However, I consider 5 sizes from 10 to 30. However, for a single size, only 4 realization. This is a random materials. However, I only consider 4 realizations, and that is a small number in a statistical analysis, as you know.
Yeah.
So maybe it's due to some random distribution of the aggregate of the material. That can be the result.
Yeah. Still strange, but for sample size 10 millimeters, the variation, as for 20 millimeters, the variation, and for the 15 millimeter one, so much smaller. Would that have something to do with the relation between the size of the aggregate and the sample itself?
It could be. I think recently there's a work doing this analysis, and they really have a very nice curve, even nicer than mine. I think they consider more realization.
Nicer in what sense?
In the sense that the curve converges beautifully. Yeah. So that confirms the effect, the correctness of the averaging equation that we proposed. In my case, only 4 realization was considered, with this actually too small for statistical analysis.
No, I'm still not convinced. Well, let me extend the question a bit further. Actually, I would be very interested in having a macroscopic constitutive law that is random, on which I can perform random computations. This macroscopic constitutive law could be derived from a statistical homogenization of the problem with macrostructure on an RBE, an RBE of particular size. So that at the macro level, I have constitutive law providing an expectation and standard deviation, and eventually also a random and special correlation. Is there, let's say, what's your opinion about the possibilities of your failure averaging technique and the fluctuations you're observing there to derive the proper size for such a random RBE from which I can derive a macroscopic stochastic constitutive law?
So you would like me to talk about the possibility of using our average failure averaging to with a stochastic effect. Then I have to anticipate that because I haven't done it yet, but I think there's a big chance to deal with this scheme for random materials to define the proper size for the RV. I think it's possible.
What would be the criterion to decide what's the size
It depends on which properties you would like to homogenize.
Because if you taking it big enough that the fluctuation, the deviation disappears, then you're not going to obtain a stochastic flow. So what size you think their way could be random enough to provide a macroscopic stochastic distributed flow?
To be honest, I don't know.
Maybe I can help you a little bit. That the strange behavior you're observing in figure 420b, that big drop of deviation for the 15 millimeter size.
So it's still
Could that be of any help?
Excuse me, can you
The
repeat
big
your-
drop of deviation
Yeah,
of the fracture energy for the 15 millimeter sample.
yeah.
Could that drop for that size be of any help to decide what's the proper size of a random RV?
No, no. No, it doesn't have, yeah. It doesn't have.
Because you explain the drop, yes, because of the small number of samples in the computation.
Yeah.
I'm sad. It's better to have found the key to my random RV.
I'm afraid not.
Thank you, indeed.
Thank you very
I'm
much.
satisfied.
Thank you. But yes, I would like to invite the Professor to continue your
Waarde promovendus, I like the simplicity of your cover, which contrasts with the complexity of the content, I would say. But I wonder whether you don't make it too complex now and then. So let's take, for instance, the example of your Sen beam, a single edge notch beam, at page 159. This is a complete beam with a discrete crack, and you use, well, this one level deeper, so to say, for the micro behavior. And you use a number of material properties there, which are kappa, gamma, beta, and the so-called C, which has something to do with the width. And I wonder, you could do the same beam, and numerous people did it by exactly computing the discrete crack path and using an engineering property, the so-called fracture energy. So, could you please explain me what this kappa, gamma, beta, and C, what they mean physically? And also, how did you assess them? How did you derive them? Or how did the experimental people measure them for this beam?
Clear the opponent. Yeah, in chapter 2, where I presented the isotopic continuum damage model, yeah, I introduced gamma as a residual stress.
As a what?
Residual stress.
Yeah, residual, yeah. Okay.
Yeah. And beta, the softening slope, the slope of the softening curve. And kappa I is the damage threshold. From that one, you have damage initiation. And I'm not from experiment or community, so I really don't know how they measure it in a laboratory. I really don't know.
But what is the physical, let's first take these three, the kappa, the gamma and the beta. They sound to me a bit abstract, they refer to a curve. Are they somehow related to the fracture energy? Or
Yeah, it's related to the fracture energy because these parameters define the softening curve and the area of that curve is the fracture energy, so it's related.
But why don't you then, looking for presentational purposes, why don't you then present the fracture energy as the parameter? Because we understand what it physically means and not these parameters.
because yeah, in this damage model, we don't use the fraction energy directly. We do these parameters. That's why I didn't introduce them. Just make it confusing.
But there's another parameter, this C. What does that mean?
The C determines the band of the localization band.
And referring to one of the previous questions also, what I can understand is when these micro cracks occur, it starts in a large volume, and then it probably reduces, and in the end you have a discrete crack where you can look right through, so it must be zero. So this C, I would expect it to be some function of the damage evolution, but you use a constant value. Can you explain why, and still you have very good results?
Yeah, you're absolutely right. In reality, the C should be dependent on the stress state or whatever, but it's an advanced damage model, and still there is ongoing research on this to develop that damage model. In my case, I concentrated more on the transition from micro scale to macro scale, so I just confined to a simple microscopic damage model.
Okay.
And you're right, C should vary in time.
But, well, at the start, the first question, maybe I can go back to that, in the initiation of this defense, you said the whole intention of this work is to simplify you can better, you mentioned it like this, that you can simply assess the parameters in experimental tests in a way simpler than macroscopic tests.
Yeah.
But how can you then do you then have a direction for this C, how to measure it experimentally? Is that really simple? Simpler than?
No. C parameters, even now in the literature, measuring C parameter is, I think, very difficult task. And usually people have to use inverse analysis that combines experimental observation and numerical analysis to define that C parameter.
But still, what do you gain then by doing this compared to the simple engineering approaches?
At least, our model take into account the microstructure of the material, the volume fraction, the shape, the size. So there's a link to the microstructure that can help you to design, but to make better materials. Yeah, there's a link. That's the gain of multi-scale analysis.
Okay, that's good. Then related to this singulation of beam, I have another question. On page page 160, you show this load CMOD diagram, and it's a bit subtle, but I see some discontinuities in that. You see at that left bottom picture there, it does not look purely continuous. Whereas the mesh is very, very fine. So, can you explain why does this happen? Does it have with the numerical stability or something like that?
This is happening because I used a quite large increment to reduce the cost. Because you know, to every gauge point along this graph, you have associated RBEs, which is again discretized into I think thousands of elements, that's why.
Okay, so these were very large steps.
Yeah.
How many steps was such a total curve to compute?
Maybe, I think, 30 something.
Okay.
Yeah.
And the convergence was very good, no problems?
The convergence is quite okay. Sometimes diversion occur, however, with adaptive scheme is resolved. Yeah.
And did you demonstrate objectivity with respect to the step size then? That if you took not 30 but 60, that you get the same results, or 15?
And I said I used that last to avoid computational expense, so I didn't do that comparative sensitivity.
Okay, well, I'm satisfied.
Thank you very much indeed. Look us through. I should continue your position.
Waarde promovendus. I'm really impressed by the sheer amount of work that you show with your PhD thesis already during the discussions that we had and going through the material that you just regularly deliver to us. I was really wondering where this guy find the time to do all this.
Single.
So it took me to the final thesis and reading your acknowledgements that I found out that you were thanking at least 25 people who apparently did all the work. But I think you're thanking too many people. I think you did really a great job. Which would bring me, because of the sheer amount of discussion that we had already, I'm not going to ask you a very detailed question, but I'd like to ask you a question about the overall result that you have. And for that, I would like you to read proposition number 3.
Just clear the opponent. It usually takes a long time for novel numerical models developed in research institute to become commercially viable.
So, why do you think that's the case?
I think that's the case because computational optimization is useful but really, really expensive. I suffer a lot.
But more, I think the proposition was more in general. Why would you think that it would take a long time for something to be that's developed on universities?
That proposition, although general, I wrote it in connection with my work. However, I think it's more or less true. For example, take the extended finite element method developed in 1999, and only recently in 2009 it was implemented in Argus. Yeah, so I think usually it should take a long time to become commercially available.
Yeah, in my experience, I think the method that's been developed should be so simplified that people actually can use it without thinking, because that's what people are actually doing. I mean, once people can just follow a set of rules, they just click and they're happy with the answer. So would bring me to my question is, how far away do you think your method, or the non-scale method, is away from simply clicking, or maybe do you see as a particular application that you think it will be worth using this method and that can be applied in, say, near future?
I don't see that, because in order for this method to be applied in a day-by-day basis, it's difficult because the users are usually the engineers, and they don't know much about computational methods. And then to use these methods, first we have to define an RV size. It's difficult, and then the method itself must be stable. And in multi-scale methods, you have to solve two problems: macroscopic problem with all the nonlinearities. We sometimes have to use arc-length method, and at the micro scale, another nonlinear problem. So I can't say myself the method is completely stable. So that's why I think it should take some time. Yeah.
Thank you for the answer.
Thank you very much. If you mind, can you give me an explanation? When is a novel numerical model no longer novel?
Excuse me, I didn't.
Well, you say explicitly in this proposition that it applies to novel numerical models.
So what was your question about, please?
I'm referring to the same proposition.
Yeah.
Proposition. It says novel numerical models. When is a numerical model no longer novel?
Numerical models is novel when it's new.
Yeah,
For me,
when does it stop being new?
when it's become popular and everyone is using it.
Thank you very much. The final opposition is for the
Dank u wel, meneer de rector, waarde promovendus. You have in your discontinuous computational homogenization scheme a microscale where you have cracks, diffuse cracks, as you say, and you solve it with a non-local formulation. And on a macro scale, you have a discrete crack. You solve that with an X-FAM scheme. So you map a local diffuse pattern to a discontinuous crack, basically. But you can imagine that there are materials that react differently, actually react in the opposite way. If you look at the micro scale, then you often see that these materials have small micro cracks, small discrete micro cracks, you would say. And on the macro scale, you see more a sort of diffuse band. Yeah? So that's an opposite type of response. In that case, what would be the best method to solve this problem? That's one thing. And how can it be objective then with respect to the RV size, which is something we have discussed very often, but also with respect to the macroscopic finite element size?
After promoter. So what I'm doing is the transition from a localization band to a macro discrete crack. And your question is just the opposite. From the discrete, microscopic discrete cracks to a macroscopic band.
That's correct.
Yeah. And I think it's possible. It's possible. So at a microscopic scale, we model discrete cracks. For example, with partition of unity method. And then when the micro cracks localized into a band, for example, to cut through the sample, and when this happens, we introduce a band, not a crack at the macroscopic length scale. I think it's possible.
And it is objective with respect to the element size, macroscopic element size, and you can get a nice RVE size, predetermined RVE size out of it.
To get an independence of the macroscopic elements, macroscopic masses, I think at the macro scale you have to introduce a non-locality. It can solve that problem. However, whether it's objective to the size of an RVE, I think it's still possible if we just do the averaging over the micro cracks that form a band, not over the entire microsample. I think there's a chance.
Yeah, okay, that sounds good. One of the unresolved issues from your thesis is the handling of a microscopic snapback, because actually this sets a limit to the size of your RVE, and as we have seen, that RVE size matters. That's very clear.
Thank you, Madam Deal. May I request the promovendus to go back to his seat in the audience, please? The committee will draw for further deliberations in the committee room. This session is adjourned.
this is what I'm going to do. But first,
Dạ vâng, thầy chú xin phép. Nhưng mà chú ấy là người Hà Lan đấy. Vâng, sang trường Sách đi làm professor. Sau rồi nói tiếng Anh với người Anh thì đấy. Dạ vâng. Em nhìn không rõ.
yeah, no, I wrote it down with I made it up. But they're not. Yeah. Okay. Ja, dat zijn gewoon een paar bitjes aan het einde al. Aan de achterzijde voert in. Op 16. Dat is wel echt warm. Ja. En dan is er een ook een wissel.
Ja. Dat was nog leuk.
Ja, leuk enemy.
Twee. van die 3, maar 2. Ja, ze exactly freedom. Doen we daar nou mee? Het model in het model. Ja, het is geen externe is je moet voor gradient damage heb je dus een
Đội trưởng đội làm nem.
đang định làm dấu hiệu chỉ tin.
Đây, chỗ này tí nữa được trao bằng ở đây. Anh Trí ơi. Hai tháng trước mà cuối năm họ có một đội cùng với người ta bảo là cũng hay nhiều quá để làm trình
anh em mai là 8 rưỡi hả?
em hẹn 8 tiếng không có chỗ để tại vì đi về hết 30 phút đấy tại vì anh sợ lửa cha nó mà trục chặt ấy thì mình còn đổi đấy được mình đi cho mình đi quá 8 giờ ở đấy thì bởi vì là 8 giờ 9 xong rồi 8 giờ 19 đều có chuyến tức là đi sau đến tận 8 giờ 29 cũng có còn thì mình là đi sớm tạo cho hay là không phải theo luôn bên Trang
Trang Từ ấy.
Trang lại Trang ấy
thì em để xe vẫn xe ở ga.
để xe ra cẩn thận để nó vạch chạm của mình.
Khi Trang này để lên cái đầu thì mình dắt xem cái chỉ nó
Nhưng mà nó có cái vạch trắng ở vẽ mình để ra ngoài thôi.
rồi nhét vào trong cái chỗ đi xe. Mày nói.
Chúng ta để đâu thì để đó. Người ta để lắm anh chị để bên hay đi tìm một
Chỗ đấy là mình là
tiền lắm
qua đây đi cái mà chẳng hiểu cái tiền đấy
có chuyện gì xe sát thì
tao 3 triệu tao chạy.
Anh sợ nhất mà Trang lên nhiều à?
chỗ nào anh sắp vào học rồi này anh bảo đi gặp chắc phải đi trên cái đầu thư của mày
Việt Nam bây giờ hay tàu học đi đó có khi một đội thì càng thử lên không anh thi trượt hay là gì đấy cứ anh nói bây giờ mình lo mai một đội cảm tử thiếu lâm sang Cameroco khảo không học tần lên thánh đều về tiên giới yên tâm đi lên trên đường rồi em thì còn có ít giống để cho cái gì mà khi để là 3% là thì tối nay không đủ
Quay tay thôi. Các giáo sư vòng xung quanh quay tay lên cái bàn.
anh tưởng cái này không
Sau đấy nè, ảnh dạ ảnh này, ảnh đấy
quay mất rồi.
bí hiểm ai xem mấy ảnh xem nó bí hiểm
Anh kêu em mấy cái ảnh nhá. Xong rồi có gì
giản dị nhỉ. Phòng
sao
màn hình tinh thể lọc.
hai ông ấy mấy ông ấy vào có tranh thủ quay tay không?
Có.
Biết ra.
Có giống trên cả không?
Đây. Phòng này.
Đây, tí nữa chỗ này sẽ là ở đây.
đâu có gì, đâu có mật thất gì trong đó đâu.
Không phải thì
cái này
đi qua
một
cái bức thất rất có là dày.
Tí nữa anh Phú ra đây xong rồi trao bằng ở chỗ này này.
Em có đi anh Tuấn.
Xong rồi congratulations new doctor. Lần trước có một anh 50 mấy tuổi ấy, ông bảo là congratulations not young doctor anymore. Buồn cười.
Chưa nghỉ trường.
À đúng rồi, đúng anh Dương bảo vậy là
đang học với chứ.
Congratulations young doctor thôi nhá.
Anh Dương trẻ tràn.
Chỉ là new doctor.
Con mới có lớp 8 chứ mà. Tôi không ngờ anh Dương có con lớp 8 rồi nhá. Con anh lớn. Anh lấy vợ rồi. Em là tầm tuổi à? Anh là con em đại học rồi.
Thế à?
Chém quá. Con đầu. Không phải đứa này. Bấm trước.
Reopen the session and request the promovendus to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft, na kennis te hebben genomen van uw proefschriftsmetstellingen en na uw verdediging daarvan te hebben gehoord, met inachtneming van de bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek, besloten u de graad te verlenen van doctor. Ik verzoek de promotor door het College voor Promoties als zodanig aangewezen zich wel van hem opgedragen taak te kwijten.
Uit de kracht van de bevoegdheid bij de wet toegekend aan het College van Promoties verklaar ik als promotor namens dat college, hier vertegenwoordigd door de rector magnificus, en de overige leden van de commissie bij deze u, Vin Fu Nien, te bevorderen tot dokter en u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ter bewijze hiervan overhandig ik u het diploma dat u recht geeft de titel dokter te voeren. Ondertekend door de rector magnificus en de promotor en voorzien van het zegel van de Technische Universiteit Delft.
The promoter's privilege to be the first to congratulate the young doctor.
Dear Dr. Vin Fu Nien, dear Fu, you just defended your multi-skill thesis in such a way that is rewarded with the TU Delft PhD title, that just happened in Dutch. The scientific world is very multi-skill nowadays. People study multi-skill phenomena, not only in our world, in solid mechanics, but also in physics, meteorology, computer science, chemistry, biology. Multi-skill is everywhere nowadays. There is an explosive growth of activities in the field and an increasing awareness also of its importance. So you are at the right time on the right topic. So multi-skill modeling is also a very relatively, I should say, young research topic. Maybe for that reason, Fu, you have one of the youngest PhD committees as well, I think. At least in Delft, it's a guess, I would say. But your thesis, your defense, will not be memorized because of that. It will be memorized for the quality of the work. You did an excellent job, Fu. You worked at the right time, as I said, on the forefront of this new topic. You also produced a number of excellent journal papers. Actually, you could not stop producing. So 2 or 3 weeks ago, you came to me, to my office, and literally begged me to write another paper, a review paper. It's a very special situation because normally it's the other way around, that we as a thesis supervisor, we have to beg the student to write the papers. At first I was not so much in favor of the idea. I thought we already published everything in the thesis. We should not overdo it. And review papers are more for key people in the field, a little bit great people as well. So we should not do that. But you were very persistent and finished the review paper as well last week, which indeed looks quite good, I must admit. So that's nice. During your period in Delft, you were a fanatic soccer player. You played in the Vietnamese team. You had your farewell game yesterday, what I've heard. Also, you were very enthusiastic football supporter. So last year you were supporting the Dutch team in your orange T-shirt. Very fanatic during the World Cup. That was good. But you very well know that a soccer game is normally divided into two halves. And the character of a game may change dramatically from one half to the other. I don't know if you've seen the Ajax Twente game this weekend. There you see it changing, and one of the famous examples is the AC Milan Liverpool Champions League final, which I think 2005, where Liverpool came back after being three goals down, and they won after penalty shootout. And your PhD period actually can also be clearly divided into two halves. I very well remember that we picked you up from what we say a non-optimal situation in France. You were not completely happy there. After you had a very successful MSc in Liège, in computational mechanics, also where you met Stefan Bordas by that time. You applied for a PhD position with us, and we had a position because it was sponsored by the Delft Center of Computational Science and Engineering. That was a project given to us because together Stefan Luding and me wrote a proposal, and we found you as a student. And I remember that we did the interview with you, and you gave a talk, and we were absolutely convinced that we hired a top guy, a potential top scorer, actually. But our new player in the team looked a bit silent in the beginning, a bit scientifically silent. You seemed not completely happy with the topic, and specific tasks we gave to you, you didn't like too much. The modeling of the cement hydration process contains some material science aspects, some physical aspects you didn't like too much. So you didn't make too much progress, and also it was a bit unclear how we could bring this multi-scale part into the thesis. I started to doubt a little bit, was this misjudgment from our side then? But this all changed half-time, after 2 years. I tried to identify later what happened at half-time during the break, what made actually the change. I would have liked to say, of course, that the motivating speech or the pep talk of the promoter, the supervisor, was actually the thing that did the job. Was not really the case. I could see three factors that played a role. We focused from then on the deep numerics and not so much on the material mechanics. So we've got a little bit about the physics of the problem. Furthermore, you were starting to use the GemJive object-oriented C++ numerical toolkit. And you really benefited from the pluses of that, I should say. And we started to work more in a multi-scale team together with Oriol. We got Oriol involved also there, I'm already there. That was good. And from the first minute in the second half, I think you lift up, started to produce, took initiative, and the PhD game changed character, I would say. Soon you got very promising, stimulating results on the new failure zone averaging scheme. You wrote your first paper. You managed to implement a robust discontinuous computational homogenization scheme, and one paper followed after the other. And now you can finish perfectly in time. Well, you used a little bit of overtime, but after 3 goals down, halfway, you did a very good job. It has become an almost within 4 years PhD, or in your case, I should say, an almost within 2 + 2 years PhD. You presented the work at workshops and conferences, luckily all in your second half, your best half. Your presentation skills went up quickly, and that was very nice to see that from the sideline. At our annual EM symposium, you were selected to give a talk, and in your session, you won the Best Presentation Award, which is very nice. Unfortunately, there's only one simple requirement for the prize. You have to be present at the award ceremony, and you were not. You went already home, writing paper number 4, so you lost the prize. Bad luck. Also, EuroC last year was very nice for scientific reasons, and it was one of the first opportunities that you could present the nice results. But since this conference was organized in the Alps, in the skiing resort, you decided to be brave and join us on the skis for the first time in your life. And indeed, I said that was very brave, and I think you are seriously happy that you survived that. Fool, you better play soccer. That is your sport. You went twice to Barcelona for a conference, and Barcelona is football heaven nowadays. So that's a coincidence probably that you went twice. But it was nice as well. You plan to go to the XFAM conference that Stefan was organizing as well in Cardiff. But luckily there was unfortunately some visa problems, you couldn't go there. But it was nice to present the work internationally as well. It was well received. Fu, to finish, you have been a very pleasant colleague, nice guy, helpful to others, also now with Amin. Amin is a new member in our multi-skill team, and you're very helpful to him. You're no longer the guy from the first half, I should say. I'm convinced that in the postdoc period, the period that you will start now, you will give second half performances. You will go to the US to work with Professor Bosch at Johns Hopkins University in Baltimore. And in many sense that will be a scale transition for you, but you will manage. In any case, I wish you all the best with your new scientific dignity. Congratulations. Thank you very much for everything you did with us, and I wish you a very bright future.
On behalf of the Board for Doctorates, I want to add my congratulations to Dr. Nghiên. He may now return to his seat in the audience, please. Ladies and gentlemen, this official meeting is over. I close the session.
Trẻ vậy đấy. Trông trẻ thế nhỉ? Trẻ kinh, siêu sao cực kỳ đã. Ngưỡng mộ nhỉ? Siêu sao á? Siêu sao đấy phải giáo sư ấy. Giáo sư ấy. Là vãi linh hồn. Ở trên Cadiz. 36 tuổi. Khủng khiếp nhỉ?
Là cái thần đồng ấy. Thần đồng.
Không, thần đồng nữa không đến nỗi, nhưng mà đại loại là siêu sao cực luôn. Chú ấy làm PhD ở bên Mỹ với ông giáo sư đầu ngành. Sau đấy chú ấy làm postdoc ở bên trường Thụy Sĩ, ở cái trường cũng đỉnh nhất của Thụy Sĩ luôn. Đó, ETH Zurich ạ. Xong rồi chú chuyển sang Anh. Đầu tiên làm associate professor trong một trường. Một năm sau trường Cardiff nó mời về làm professor. Trong thời gian đấy hàng loạt các dự án của châu Âu chú ấy đều làm đứng tên hết.
Khiếp vậy. Nó làm về gì ấy?
Computational mechanics, phần toán đấy. Cũng là trên nhiều ngành khác nhau. Chú đấy á, chú đấy Stefan Bodas, người Pháp. Người Pháp.
Anh qua tin nhé.